fine-grained tracing without binary instrumentation. Or I like to say, don't be a pinhead, think outside the box. And this subtitle is a joke. People that use pin, this tool I'll be discussing shortly, are called pinheads, self-described. And an emulator for x86 is called box. So it's kind of a joke, and I'm not using these technologies because it's really cool to use these dynamic instrumentation tools like pin and Dynamo Rio. So we'll be talking about how to achieve binary instrumentation or run tracing without binary instrumentation. So really quickly, about me, as Thomas said, this is my first talk ever, so don't believe anything I say. You guys probably know more about this topic than I do. I graduated from school in 2008. I used to work at Symantec in their security response team. I interviewed with iSight partners at Black Hat Vegas in 2009, and I started work in 2009 at iSight. Reverse engineer, hacker, whatever they need me to do. And as you'll see, work is in italics because I really just like playing around with shit. And this image here I have of myself is actually one of my colleagues named Greg McManus gave a talk at Black Hat called Uncode, and he released a technique to encode images with shellcode. So if you use my slides in any of your exploitation, you can just jump into this image and it will actually create a shell back to my box. So do that. Okay, so today we're going to talk about execution traces. And if you guys don't know what execution traces are, probably not going to understand anything I'm going to talk about today. So I think they're extremely valuable. With execution traces, we get a lot of different things. And today, I'll be explaining how to get good code coverage and all these issues here. So why do we want to do execution traces? If you guys don't know, specifically at iSight, we focus on these three things here. Exploitability, why did code crash? So if we have run traces of execution, we have a better story of how the code is executed when it crashed. And we don't just have a stack frame. We want the entire trace of what was executing at the time, how it got there, all the way back from when it started, when the program began. Obfuscated malware analysis. So if you're looking at some code and you have no idea what it's doing, it's packed, it's obfuscated, it's encrypted, it's using some weird virtualization scheme that you don't know what it's doing. Run traces will help you to understand how it got to where it was when you're analyzing it. Also reverse engineering. If you're looking at things and you don't know how they're working without an actual run trace, it's difficult to explain to people what's going on. So with execution traces and IDA, you can combine the two and use it as a great reverse engineering tool, which I'll be talking about. So you can use execution traces to enhance and enrich your reverse engineering lifestyle, is that what you call it. So the tracing types that you'll see people talk about, actually the next talk goes into the first bullet point here, is there's so-called coarse-grained tracing, which is at a syscall level or an API level. So what that means is your program's executing and you're just going to keep track or take notes at each function call. So you'll know, let's say this malware sample is calling create remote thread. You want to just keep track of every time you call a create remote thread. That's so-called coarse-grained tracing. But today we're focusing on fine-grained tracing, which is at the instruction level. So I want to know every instruction that was executed. And this is also, this term basic blocks, you guys are familiar. It's a way to think about, how would I describe basic blocks to you guys? It's a way to think about the code at a level that once it enters a basic block, it has to go through the basic block in order to get to the next basic block. So you can think about it as logical chunks of execution that have to take place. So you can break these chunks out and say, the code will enter this basic block and will exit this basic block. And you know if you hit the beginning, you'll hit the end. So it's a way people commonly use basic blocks to optimize code, to do code coverage analysis. So it's just a way to classify instructions into logic blocks, I guess you can think about it like that. So today we're going to talk about fine-grained tracing and this new technique I developed to do that. So before we do, a lot of people use dynamic instrumentation. So dynamic instrumentation is a really powerful technique that you can use to do a lot of things, commonly profiling code. In school, I used Fine-Gerained actually to, my teammates would submit code that was buggy, and you can do some profiling in Fine-Gerained to figure out where memory leaks are. And specifically for run traces, people use dynamic instrumentation as a way to keep track of what the program is doing. So these frameworks allow a very easy way to, at an instruction or basic block level, to have a callback that you can just take notes every time an instruction or basic block happens. And that's great. There's downsides to this though, which I'll be talking about today. And this whole talk stems from why these tools don't work for specific situations. So they're great. Pin and Dynamo are amazing tools, and they have sample code on their website that you guys can go download, and you can create your own tracer in no time. There's very simple calls you can make to register a handler that will be called every time a new function or basic block is called. So you can have a tracer from 0 to tracing in no time with dynamic instrumentation, and that's the minimum. They do so much more than that, and they're very powerful tools. But for my needs, I need to keep track of how a program is executing at a instruction level, and for reasons I'll explain, when you instrument a binary, it has adverse effects on how it executes, it has adverse effects on if the binary is checking to see if it's been modified. So this is a problem for self-modifying code and for code that checks on itself to see have you injected any breakpoints or has the code changed at all. So dynamic instrumentation is out for my needs. So I had to come up with a solution, which we'll talk about today, to do run traces without using binary instrumentation. So without modifying the actual binary itself, how can we record its trace of its execution? So today we're going to talk about that. And if you guys have any questions, by the way, about the stuff I'm talking about, please interrupt me and ask questions. So I've listed here some dynamic instrumentation tools, like I was saying. Pin, Dynamo is the most popular. Fine-Gerained has been out for a while, and Microsoft has a .NET profiling API. And there's other solutions as well for essentially modifying the binary to do what you want at specific times. I guess that's how you can think of instrumentation. So specific for tracing options, if you want to, like I was saying, if you want to trace execution, how do you do that? Traditionally, you have these options at hand here. You have APIs that your operating system will expose. ptrace is one we're not going to talk about because I'm focusing this talk specifically on Windows because that's where all the money is. Debug active process and wait for debug events are Windows APIs you can call to trace or to debug a process that's running in Windows. You have debuggers you can use. EDB is one of my buddies, Evan's debugger on Windows or on Linux. You have WinDebug, which sucks, and you have OllyDebug, which is great. Clicky, clicky, clicky. And you also have specialized tools that you can use to trace execution. Pedram came out with Process Stalker in 2006, which is now called PayMe. It's I guess you can think of it as a fuzzing or reverse engineering suite of Python and other tools. And you have this coding trace suite that the Grub put out. So there's options you have out today to do tracing if you want to get good code coverage analysis, you want to do malware analysis. There's options out there. But the thing is, all of these solutions, they modify the binary in some way, which means that I can code the binary to detect that and then not execute or do something different to change how I will achieve my goal. Which is very important if we're doing malware analysis. And the malware itself is checking if it's being watched, and if it is being watched, it doesn't do anything. Which is a huge problem because you have a lot of these malware shops that do virtualized or emulated execution, and they might see, I've heard somewhere like 10% of their samples might do detection of some tracing or virtualization or emulation, and they won't execute, or they'll do something different if they detect that they're being watched, essentially. So today, again, we're going to talk about how to achieve the granularity that these tools provide, but without modifying the binary at all, thanks to Intel. So common methods that these tools will use, if you guys aren't familiar with how tracing, how you could actually, if you think about it, how you could actually trace how a program is executing. x86 is my provide a way to detect or to do tracing of a binary. I know that's a whole explanation. If you guys are interested, we can talk after this. You can inject breakpoints, so you modify the actual binary itself, which is what a debugger will do. It will inject code into the binary itself, which modifies it. There's hardware breakpoints, so a lot of the processors you guys might use will have facilities on the chip to do breakpointing, which will not modify the binary, which is kind of cool. You can also book functions, so if you're interested in creating your own thread, you insert a jump at the beginning of a function that jumps to your function, and then you take notes and you say, okay, this function was called. And question mark, you guys might know of more ways to do tracing. The options are amazing. There's a lot of cool techniques to do tracing at every level, and I'm here to talk to you today about a specific Intel option for tracing. So why am I up here? Again, I've shown you a bunch of techniques already. You can use dynamic instrumentation, you can use debuggers, there's all these tools already released. Again, we need to achieve reasonable performance, and we don't want to modify the binary at all, and we want to not be detected with current techniques that malware and bad guys use to detect. So that's why I'm up here, is to explain to you guys this technique that I probably should be talking about, because I'm hoping that the arms race is not brought to the next level and malware starts now checking if my technique is being used. So I'm going to explain to you guys how to do an awesome run trace without modifying your binary at all. So the limits of current tracing techniques for advanced malware analysis and for code that's checking to see if it's being monitored. So there's checksum in code that checksum itself that's executing, and if the checksum fails, it'll exit. Skype does this. Self-modifying code, you'll see a lot of malware these days that uses the stack to do some calculations, and it will modify itself based on those values. So if you fuck up the stack in some way, the code will just crash. Debugger detection, there's a lot of papers out there, I'm sure you guys have read, how you detect if a debugger is attached. On Windows, it's really easy. Virtualization detection, there's a lot of easy ways to detect if you're executing an emulated or virtualized environment. And companies likely pay analysts to handle these specific cases by hand, and I don't have time to do that. So we created this tool to essentially run these samples that if our malware lab comes back and says it doesn't do anything, we just run through this tool and see if it does anything on hardware with tracing it with this technique I'm about to describe. Also, I'm very impatient, and potentially we have millions of samples to run, or to trace a few samples prime millions of times. And a lot of the tracing options are very slow because they might break on every instruction, or they might use other techniques that are very slow to execute. So we need to achieve some reasonable performance while also hiding from the samples themselves without modifying the binary. So these are the limits that we will overcome today. Also, a quick aside here. A lot of the samples that I see daily that are run in sandboxes are checking to see if you have modified the library calls at all. So this sample here, this is just some output. It's actually comparing the beginning of load library A to see if there's any jumps. Okay? And if there are any jumps, it does something different, which is bad. We want it to do what it was originally intended to do maliciously. And so here, if it detects that there's a jump, it will just exit or whatever. So that's unacceptable. We really, these cases are screwing people that use detours type hooking in their libraries, and it evades the detection of whatever tracing suite you're using if you're specifically looking at malware. This next sample here is really sweet. This one not only detects that there's a hook, but it just overwrites the prologue with its own prologue. So it'll just essentially screw your hooking, and just it knows the prologue of the function it's going to call, load library, and it will just use its own prologue, which will effectively overwrite your hook if you have a jump at the beginning, which is a common technique that detours, which is a Microsoft thing, or people who hook by hand, they have jumps at the beginning of these functions, and this will just insert its own prologue and do its thing. So you're effectively blind if you're relying on your hooking at the library level, because these samples detect the hooks and just overwrite them. again, this is you can also detect this and hook later or different places, but this just goes to show how painful and annoying it is that these things these samples are doing. They're really screwing with us and making my job more difficult, which I hate. So again, this just goes to show why when you come up with a solution that doesn't rely on modifying the binary, it doesn't rely on hooking other libraries to watch what's going on, because as you can see, it becomes a pain to make sure you're actually getting a correct run trace. So this one guy in this community came up with this talk that said there's a party at Ring 0, and it seems like really exclusive. Everyone, Ring 0 is like the hotness, it's kernel land, all that good stuff. Is it exclusive? No, I'm some kid, and I'm about to describe to you guys a Ring 0 tracer that's really easy to implement, that you guys yourself probably implement. So it's not exclusive at all, thanks to Intel. So Intel has a lot of awesome debugging and profiling microcode, I guess, built into its processors, or microprocessors. And one of the things that I'm using extensively in my tool is called last branch recording. And if you have volume 3B of the Intel manuals, it goes into extensive detail about what last branch recording is. But today I'm going to talk about it specifically, how I use it in my tracing. So the last branch recording mechanism on Intel is implemented in a couple different ways. So essentially, you can think about it, every time an interrupt happens, or a jump happens, or a far call happens, the processor is effectively a branch, think about it like that. And the Intel chips that I'm using specifically have a mechanism to record them. They have a capability to record branches in microcode, which is amazing. And it's implemented in a couple ways. So the first one is the last branch recording stack, which I believe allows you to record, I think there might be Intel people in the audience. If there are, correct me if I'm wrong, I think it allows you to record 7 of the last branches. Again, I don't use the last branch recording stack. It's just a really effective way, or a quick way to keep track of the last 7 branches you took, which we'll talk about this later. There's also the trap on branch. So every time a branch happens, the trap flag will be raised, and then a debugger or some other code can then handle that and process what's going on. This is what Process Stalker uses. It's called BTF. It effectively speeds up run tracing. Although I don't use this because I find that when we were reading over the manuals, the trap on branch thing seemed too slow. I didn't want to, every time a branch happened, have to handle it if I'm just trying to record what's going on. So it seemed like all the context switching would be cost intensive with time. And they have this awesome thing called the branch trace store, which is the facility that I'm using in the tracer today. And it uses the debug store facility of Intel chips. And there's 2 ways you can set it up that I'm aware of. You can set it up in a cyclical buffer, so which means you tell the processor, okay, I have this buffer to record branches, and it'll just overwrite itself, and you have to, on your own time, I guess, copy data out of the buffer. And in that sense, data might be lost, which is unacceptable because we want accurate run traces of whole program execution. So there's this interrupt-based thing that they provide, which will trigger a counter overflow when the buffer is getting full, which is great because that's essentially a callback. I can register an interrupt handler, and when the buffer is almost full, I can then copy data out of the buffer with the local interrupt controller. And then there's also a great thing that they added, which really improves performance for me, because in this talk we're only discussing userland application tracing. So you can set up the last branch recording to only trace the OS, or to trace userland, or to do both. I believe you can do both. So I only turn on the userland tracing, which means I don't care when context switches happen. I don't care when kernel code's running. Some other analysts might, but for my purposes, I'm trying to trace userland apps, malware, etc., before they inject stuff in the kernel, before they do anything in kernel land, and to find bugs in userland apps. So I specifically use the userland last branch recording and the branch trace store. I know this is going to be a lot of acronyms, a lot of junk thrown at you guys, so if you have any questions, again, please ask. So I'm going to talk today about NetBurst, which if you guys aren't familiar, it's the P4 and Xeon processors and some more, and they're really old. And the reason I'm using this architecture is because we had these boxes lying around in our lab, and we just grabbed one and started working on it. And unfortunately, these aren't architecture or model-specific registers. These are implementation specific, meaning this changes based on what architecture you're using, which is unfortunate. I think that's changed in the newer ones, and they're always going to be the same now, but these bits are different on your Intel processor. So specifically, I'm using model-specific registers to turn on the last branch recording facilities. And as I'm just demonstrating here, you have all these options to configure your last branch recording. And I kind of already went through with you guys how there's different facilities that you can enable and disable, and this is the MSR that you'd use to do that. And specifically, I wanted to show you guys that it's kind of cut off on the top, but that just says debug store. That's a facility that you have to set up in memory, where the microcode will then store the last branch recording branch records in. So you have this DS buffer management area, and before you enable tracing using last branch recording, you have to set up these values in memory. You have to set the buffer base, you have to set the buffer index, the absolute max of your buffer, how big your buffer is in memory, and your interrupt threshold. And then below that is a bunch of, I can't remember what that stands for right now. It's escaping me, but it's a precise event-based something or other. Anyways, it's junk, and I'm not using it, but PEBs and BTS both are implemented in this debug store, so you have to set this stuff up in memory. And then this BTS buffer you also have to allocate in memory yourself, and then the microcode will start storing branch records here very quickly, which is awesome. And then you copy them out of the buffer here. So it's implementing this tracer. It's an exercise in figuring out the values that you want to use for all these things. How big is the buffer? What is your interrupt threshold? How long is it going to take you to copy stuff out of this memory area and into your network driver, your serial port, your user LAN? So it was an interesting exercise in buffering here and figuring out the right values for all these things. And if you guys want to talk after my presentation, you can kind of talk about some of the values I use for the specific implementation on NetBurst. Obviously, these values will change if you're using multi-core CPUs. So this is just a stolen diagram out of the Intel manual that I presented here for you guys to see. And then the branch records. So I'm tracing stuff, right? And the traces are actually just branch records that the microcode is writing to memory. So what I have is the last branch from, the last branch to, excuse me, and if the branch was predicted. This branch prediction stuff could be pretty interesting, but for the work I'm doing, I haven't really found a use for that. If you guys come up with an idea about how we could use the branch prediction and tracing, that might be cool. And the addresses that it's storing, the last branch from, last branch to, the Intel manual will say that they're linear addresses. And originally when I was implementing this, I thought linear meant the actual hardware address, but it's actually, after segmentation has been applied, so it's actually, I don't want to mess this up, it's actually the virtual address, I believe that's the right terminology. Anyways, it's specific to the actual context of the application I was running, which is really great, so you don't have to do any weird page table stuff. It's pretty awesome, a really great facility. So now, I kind of breezed through the Intel's facilities for doing tracing. And if you can imagine, on Windows, which is our OS of choice, implementation becomes an issue because Microsoft doesn't provide any facilities for turning this stuff on and off for specific threads of interest. So essentially, we had to hack the kernel to turn this stuff on and off for us when we wanted to, because we only care about specific threads of specific processes. So we can't just turn it on, get all this trace data, and then filter that out. We have to, on a per thread basis, turn on and off the last branch recording, which is the next part of my talk. I'm going to get into how we implemented this in Windows. And this is my IDA setup. It's really bad to show on the slide. It's black and all this shit. The important part of this is that we decided to hook a specific function in the kernel that handles context switching. It's called swap context. A lot of people hook it. Kaspersky, I think, hooks it. It's a great vantage point into new threads getting time on the CPU. And you get to see the oncoming thread and the thread that was executing at this point in code execution. And Microsoft was really nice here, and they gave us these nice 7-byte no-ops. So there's this great code area here, which is interesting. And then this first instruction in swap context, which you can't see at all, is well, luckily I turned on my IDA dummy comments, which is great. So they have this logical inclusive OR, this first instruction, which is effectively useless. So it almost is like Microsoft wants people to hook their swap context function because they provide this facility. So as you can see in this next slide, what we did is you just overwrite this OR with a jump short. And so I jumped back up here into the knobs that they had and overrode it with another jump to my code here. So Microsoft provides you a nice facility to patch their swap context function. This is on 32-bit XP. I know on 64-bit machines they have their patch guard stuff, but that doesn't. We're not doing that. This is XP on 32-bit. So this is a great way to get perfect vantage point into what threads are about to execute on the CPU. And again, you will be wondering, well, didn't you just say that the code is checking to see if stuff is patched and then doing something different? And yes, it's unfortunate, but we had to do something in the kernel to turn on this last range recording. So we had to put a hook somewhere. But luckily, we're still tracing userland apps, so they can't just directly read memory at the beginning of swap context and see if it's been patched or not. So hopefully that provides enough protection, I'll say. Okay, so again, like I was saying, this is a Windows implementation, and the way I developed it was kind of like malware, since Microsoft on XP has 2 different kernels, one for physical address extensions and one without. So patching becomes an issue if you're trying to make this tool work across with different kernels. You need to know which values and they're going to patch, right? So what's commonly done is people will scan through memory for a fingerprint of the function they're looking to patch, and that's lame because if they change that, then your code is broken. So what we do is we use symbols, and we're checking the symbols of which kernel you're running to see if you're using a kernel with PAE or not, and then there's a system call you can do in the kernel to get the offset of a function, and then we just compare the symbols with the return offsets, so I know exactly which value to patch. So anyways, we have this userland portion of the code that drops the driver and then creates the service that runs the driver. And then the driver code itself, like I said, it patches swap context. And then based on the threads of interest, we'll turn on and off the tracing. And here's a nice little diagram I threw together to explain this at a higher level. So you have this userland application that tells the Windows driver which threads we're interested in, and then it will, when the thread is about to get time on the CPU, we'll turn on tracing through the MSRs, and we'll set the APIC to tell us when the buffer is almost full, and we'll copy data out of userland back, copy data out of the kernel back into userland, which is all the tracing. There's a lot of caveats here. If you read the manuals, there's a ton of crap you have to set it properly, which I didn't really do, but it works. There must be separate save areas, buffers, and state for each processor and multiprocessor system, which seems really complex. But if you think about it, it's actually easier if you have a specific buffer per thread. So you can create a BTS area for each of the threads, and then once you're done tracing, you have a nice thread-specific trace log. So the multiprocessor issue doesn't become that great because you have a per thread buffer anyways. Also, a nice little caveat, on Windows, they like deferred procedure calls, and I didn't really account for this when we were testing, but when an interrupt is raised on the CPU, and before the deferred procedure call gets time to run, the malware or the